Another DraftScience video presentation. Yay. Comments, and we'll see where we go from there. Pretty much, this will get easier and easier for me to point out, exactly focus you on the facts that make it understandable why they are wrong and what they're doing to be wrong. All these critics, defending the religion of VmV. I mean, it's on its face, doesn't make much sense. Why is velocity twice important? Why? What's the logic? How can it make a difference? And you can sort of understand it in the momentum argument, right? I mean, we'll probably do this later. Let's just follow the momentum, right? I mean, you know that when something hits something, it exchanges, and it has to exchange based on how fast the thing's going to leave. And the thing can't leave faster than the thing that's going is going. So it can only impose so much energy, and that energy has to go away from the thing that has the energy. You can't give it energy and still have the energy, right? The thing that's moving can't still have energy and make something else move. If it makes something else move, then it has to lose some of its energy. And there's just no way to make this mv squared thing make any sense, because it means that some object with a certain amount of momentum somehow is going to make other objects have even more momentum. When I add it all up, there's going to be more momentum, more energy than the thing started with. So it's that paradoxical, and it's kind of overt and obvious, and yet they just keep, twisting and bending to try to force it to make sense. So this guy, Bob Stay, all right, so I've made these three little arguments: the bowling ball argument, the shoot things up into gravity argument, and the train argument. And they're obviously create paradoxes, and they obviously haven't explained any of those. And they keep explaining them with what this guy's going to do, which is completely screw it up. Okay, so anyway, if I shoot two objects of opposite with opposite velocity to mass ratio, so one is 1-2 and one is 2-1, okay, into gravity, your formula says one object will have twice as much energy as the other at liftoff. So perfectly true. So let's just draw it so you understand it. It's not that complicated. Okay, same spring. Okay, compression. Okay, I shoot two objects with exactly the same amount of spring energy. One has two masses and one only has one mass. Okay, now the spring will, because this is less mass, the spring will move faster. It will give this object twice the velocity, 2x velocity. Okay, so this one has two velocities. This one, because it's heavy, the spring will move slower. Okay, I don't know how to draw slower, but it'll move slower, okay? Which means this one will have only one velocity. Okay, so this one's going to have two velocities, okay, and one mass, and this one's going to have two masses and one velocity at liftoff. That means, by their formula, because you square the velocity, right? You square the velocity. So squaring 1 doesn't get you anywhere. Squaring 2 gets you 4. This one's going to be 2 times 1. It's going to be 1. So this one has 4 joules. This one has 1 joule of energy. Whatever unit you want to use, doesn't matter. It's all the same thing as we've gone over and over and over before. Units doesn't make any difference. They're just for comparison. So you have 2 to 4. So this one has twice as much, technically, energy at liftoff. That's undeniable. Frankly, that's what will happen. If I use a cannon, and I shoot a cannonball, the lighter ball goes further. Okay, I put a twice as heavy one in. Oh, it doesn't go as far. It's just a fact. All right, so we know springs work. We know they work just as good as cannons. Anything else we use, we know we're going to get more velocity out of this object because it has less mass, and we're going to get less velocity out of this object, which means they can't have the same energy at liftoff. Impossible. But the fact is, when they land, they're going to compress the spring exactly the same amount again. So momentum works all the way through. Momentum says equal. Momentum says up here equal. Yes, one will go higher because it's lighter. The heavy one won't go as far. So what? It's gravity, okay? They won't go as far into a magnet. They won't go as far into a lot of things based on mass. So, but the fact is their momentum is always the same. All right, so their momentum, not through the path. Okay, you can't pick a location and say they have the same momentum here. That wouldn't be true. But the point is they have the same. They're putting the same energy into gravity, and they're going to get the same back from gravity, because that's how gravity works. It's a conservative force, as they call it. Okay, so whatever you put into it, you're going to get back again. And the simple truth is when they finally reach their maximum velocity, as they're coming down and they're going faster and faster, and they reach their maximum velocity, it's going to be exactly the same as their velocity they left with, minus air resistance and whatnot. 0.9% of what it was, okay, when they left. It's not the way I want to say, it's 99%, I'm just saying. Anyway, and they're going to compress the spring exactly the same. So momentum makes perfectly good sense. It explains the phenomenon. Everything makes sense. It makes absolutely no sense to say when they left, this one had twice as much energy. But it won't produce twice as much in the battery. The battery won't collect twice as much. Just like the trains, just like the 5-ton train and the 10-ton train. If I tried to collect the energy off them with a little generator on the wheel, I'm going to generate just as many watts with the 10-ton train going 5 miles an hour as I am the 5-ton train going 10 miles an hour. They'll give me exactly the same energy. This will happen. It's the same energy. There's absolutely no good reason to have this imaginary fable that somehow this one has twice as much energy when it took off, and it has twice as much energy when it hits the spring, but somehow the spring can't find it. It makes no sense. It's all a fable. It turns in. They might as well just be telling you this one turned into a gremlin, okay, and then it flew through the air as a gremlin, and then it came back down. It's still a gremlin, but all of a sudden, as soon as it hit the spring, it disentangled and became a non-gremlin. I mean, it's just a story they tell. It has nothing to do with any physical reality. Okay. So it's simple enough scenario, right? I mean, there's not too many moving parts here. It's not too confusing. It's not that you can't fuck it up too much. He fucks it up. So here's the fuck up. Okay, there is no formula that says that. I just pointed out that's exactly what mv squared means. This one the lighter object has to leave at twice the velocity. The spring is saying so. The spring says I have 100 joules of compression. It's saying I'm giving it to you. The only way you can defeat the spring is to put something so light on the spring that it's lighter than the speed at which the spring can release, its maximum speed. Okay, so if it requires a velocity that's faster than the maximum speed, the free speed of the spring, then obviously it can't put the energy into the object, because the object will leave before it can finish putting the energy into it. Okay, but there's absolutely exactly what your formula says. So this is just fail, whatever the word would be. You can't do this. You can't premise your argument with false notions. There is a formula. It's the formula you're defending. Okay, compressed springs store potential energy. It doesn't matter what you call it, potential, you could call it frog pie energy, you call it any kind of name you want to call it. The fact of the matter is that we know it's stored energy, okay, and it's the same energy that's going to happen when they land. It's going to restore the energy. Well, anyway, so he says, first premise, here he is, right, just from the start, you might as well just say, forget it. Okay, he says, both masses will leave with the same kinetic energy. Your theory squares the velocities. They can't leave with the same velocity, so how is it possible for them to have the same kinetic energy? It's impossible. Okay, but different momenta. How is that possible? So your premise is obviously just completely wrong. So we're already done. There's really no point in reading the rest of this, right? Because the premise is completely wrong. They leave with the same momentum. Okay, and by your formula, they have different kinetic energies. The spring can't produce different kinetic energies. It can only produce the spring's energy, the number of joules of compression. All right, so just a silly premise. Okay, both will leave with the same kinetic energy. As I just pointed out, this one's going to leave twice as fast. And if we have to really argue about that, then what's the point, right? I mean, if you can't get the idea that the lighter cannonball goes further, there's no conversation, is there really? I mean, there can't be. They obviously can't have the same kinetic energy. They can only have the same momentum. All right. Okay, they will both reach heights inversely proportional to their masses. How can they possibly do that if they're going the same speed? The only way they can have the same kinetic energy is they have to be going the same speed. They're not obviously not going the same speed, so they can't have the same kinetic energy. You don't even understand. So how can they go different heights if they're not going the same speed? I mean, it doesn't make any sense. Okay. To their masses as they convert KE to PE, miles per hour. So whatever. They're obviously nonsense. Okay. They will fall back again and regain the same kinetic energy. Well, again, the kinetic energy by calculation. They can't go higher unless they're going faster. So we know that. So there's no way to go higher if you're not going faster, right? You do understand that, right? Maybe he doesn't understand that. But anyway, they will compress the spring the same amount upon impact. So again, it just doesn't make any, there's no other way. I can't explain it any other way. I can't start with your premises. How do I put different, the same kinetic energy into them, okay, without somehow, you know, doing something impossible? I mean, what do I do? I make the heavier mass go faster? I mean, how can I give them the same kinetic energy? It's impossible. All right, anyway. So I'm not even going to read the rest of this crap, because what's the point? So he says here, the point, however, is that spring PE, object KE, object PE, object KE, this is all just such bullshit. They have energy, momentum. Okay, this is this KE, PE, what is this bullshit? They never have potential energy, by the way, okay? So, I mean, again, people who like science, they ought to be at least a little bit scientific and recognize an object never has potential energy. Okay, your chemistry can have potential energy, but the object, how the fuck can the object have the potential? The potential is the fact that you're, going into the rain or going away from, with the rain or against the rain. You can go with the stream or you go against the stream. It doesn't mean your boat has any fucking potential. Okay, when the balls fall back to the spring, the exchange of energy and momentum will be the exact reverse of what happened at launch. Right, and what happened at launches is one's going twice as fast as the other. I mean, one's going faster than the other. Yeah, twice as fast, actually. And by your formula, that means it has twice as much energy because you square the velocity. Okay, so everything will balance out. There's no balance. The whole thing is silly. So I'm deleting your comment until you start with a rational premise. Okay, so fix number one because it's complete nonsense. Both masses will leave with the same kinetic energy. They can't leave with the same kinetic energy unless they're going, like I said, what do you have to do to the speeds to make the same kinetic energy? Let's figure that out, right? Okay, so they obviously don't have the same kinetic energy when they leave because, so the one mass has to be times what to have the same kinetic energy? Well, I guess that they're okay. So it has twice the velocity. So the kinetic energy is 4 joules and 2 joules. So I have to inverse the velocities, right? Well, let me pause and figure that. There's no point in me wasting your time. All right, so I'll pause and figure it out. All right, back. Yeah, so it's this 1.4 number. I should have remembered that. So to have these equal the same thing, okay, to have the same kinetic energy, this object, the lighter object, for some reason, has to leave at 1.4 velocities. So it has to leave a little bit faster than the two mass object, but certainly not the expectation of the joules. I mean, it's not the same number as what the spring is saying. The spring isn't saying that. So it's still, what does that mean? Where do you have any evidence that anything ever leaves at this number? So instead of going twice as fast, they're saying it goes 1.4 times as fast. So again, they're saying if I go to throw an 8-pound bowling ball, somehow I can't get my arm to move faster. I can't get my arm to move twice as fast. And I can only put 1.4 times the speed of the 16-pound ball. So even though I went twice as light, I somehow can't get twice as much speed. So I think, you know, again, they have zero evidence of this. So this is the assertion he's making. And there's just zero evidence that that's what happens. The spring, this leaves with twice the velocity because it's twice as light. This one leaves with one velocity because of it, you know, it's twice as heavy. That's the truth. This is fake. Okay, and the train sort of example does prove it. Okay, I drop twice the mass on a train, right? I drop a mass that's twice the mass, that doubles the mass of a train. The fact is the train moves at half the velocity, not 1.4, half. Okay, so this number, until you produce one shred of evidence that this is how it really works, you can't keep saying it. You have to actually, you can't keep asserting it's a fact. This is what we disagree about. Okay, I say that's 100% inaccurate. Okay, absolutely never happens in the real physical universe. So until you demonstrate that the same spring can't make the half as light object go twice as fast, this is hopelessly bullshit, frankly, from my perspective. You have zero evidence of it. You've produced no evidence of it. So you can't keep asserting it as a fact until you produce some evidence of it. Yeah, that's the way to say it. All right. So I thought there were other comments. So this is a thread that I already completed. Where's the other comments? I guess the other guy bailed out. There should be another comment here. Oh, this is the wrong video. That's what's wrong. Okay. Somehow I'm in the specific video comments. That's not what I want. I want this. All right. So now we have, this is another new comment. So I haven't read this yet, but we'll see. Interesting note. Momentum. Noun. Oh, in 1690, the scientific use in mechanics, product of the masses and the velocities of a body. Well, obviously, 1690 is really late, okay? So, obviously, momentum was used by Descartes in, like, 1620. So, blah, blah, blah. Quality of motion of a moving body, from Latin momentum, movement. So, the word momentum was invented then, okay? But they called it quality of motion before that, so it doesn't make any difference. Moving power. Figurative use, force gained by movement and impulse, impelling force, dates from 1782. So again, these are just, you know, I don't see much use in going into this stupid word game bullshit about when they actually started calling something a specific word. The point is we know MV is 1600s, early 1600s. And MV square is mid-1600s. Not that big a difference. All right, power as in energy, safe to say. So this was an early controversy. They're both old ideas. One of them, I'd say, obviously has a terrible history in the sense that it started off as MV squared, no half in front of it. So we already know it was wrong. We also know that Newton's mechanics worked perfectly. So, you know, outside of Mercury, you know, which can be explained by the sun processing, outside of that, Newton's mechanics works. So why do we have to fix momentum? It worked. Oh, that's right, we don't have to fix it. And the only reason why somebody tried to fix this is because he didn't like Newton, because he didn't like Newton's mechanics were too ungodly. There wasn't enough God in Newton's mechanics. So again, these people who are fighting so aggressively, you're just fighting for religious dogma. You're not fighting for a science. You're not fighting for the truth. You're fighting for people whose intent was to force science to meet their metaphysics. They wanted the world to match their worldview of their religious notions, their free will ideas. So that's all you're doing is defending religion. All right. Okay, so this is the comment I just read. Which, yes, I mean, you know, I read the whole thing, so I read all this little babble here, but there's no point. This babble means absolutely nothing because this is all falsely premised. So it's falsely premised on some notion that the lighter object only goes 1.4 times as fast. And everybody should know that's not true. Okay, so delete. Delete. Thank you. All right, so this guy's just this is just probably the cowboy. It's not really that, you don't have to work too hard to be, until I insult your mother, you really don't have a right to insult me. Even if I've insulted some friend of yours, you really don't. So you have to really learn how to be a little bit more civil. I don't, again, I have expectations when I'm having a conversation on Quora or something. I know I can't tell, I can't start attacking the guy in some personal way. All right? Or I'm going to get banned. Those are the rules, assholes. You know them. You just don't care. Okay. So he says a 2-liter bottle of water dropped 1 centimeter will achieve a speed of approximately 1 mile an hour upon impact. I would say that's agreeable. So we're talking about 7 pounds or so of fluid. Okay. A dime, 2 grams, traveling a dime, 2 grams, which is like a 9 millimeter is like 7 grams. So it's 1/3 at least of the weight of a 9 millimeter slug. At 1,000 miles per hour has equivalent momentum. Agreeable. Yes, if you do the calculation, work the numbers out, you'll be able to go from 2 liters at 1 mile an hour right down to 1,000. I mean, 2/1,000ths of a kilogram. I mean, at 1,000 miles an hour. Okay. I mean, the grams is 0.002 kilograms. All right. The water bottle cap and the dime have equivalent contact area upon impact. Well, I think everybody knows that's not true. So that's, it's just not true. I mean, a dime is pretty small compared to the cap on a 2-liter bottle. But anyway, let's just make it the same size. Or let's do we can do different things, right? We could just say we're going to hit a hypodermic needle with both things. So we're going to stick a hypodermic needle right on your chest, and then we're going to say, which one do you want to get hit by? The 2-liter bottle moving 1 mile an hour, going like that. Or do you want to get hit by the tiny little 2-gram thing, going 1,000 miles an hour? Which one would you rather have drive the needle into your chest? I mean, you just, science is science. You want to play. See, they just want to play like Ken Wheeler. They just want to play visual games and pretend we're not smart enough to, follow the real science. And the real science is they're equivalent. Now, okay, it's hard for you to see it that way, but I already gave you the example. I mean, me handing you a bowling ball is the same energy as, a bullet, a 9-meter slug. Same energy. All right. Now, obviously, one of them's, not at all inconvenient, barely inconvenient. Okay. And the other one is going to kill you. Well, it's just because of the shape and because you've changed the mass to velocity ratios, and therefore it's going to penetrate different and do lots of things differently. It's going to interact with different bits of your energy in a different way. Your matter. But that's all you're doing. You're just reshaping something and then saying, because I reshaped it, it means now it is fundamentally different. And so I could just argue that, bulletproof vests, if I shoot, a dime would be less than a 22 caliber slug. So a dime is less than a 22 caliber slug. Now, no cop wearing a bulletproof vest, they're barely even going to feel a 22, when it hits the vest. It's not going to leave a mark, nothing. Because they're going to spread out like a dime. They're going to take that slug and spread the energy over a large area, and it's not even going to, the cop, he's not even going to notice it barely. It's going to be like a 2-liter bottle hitting him. So what? No big deal. Okay. Which one would you rather have traveling towards your chest while lying in bed? Well, go ahead and try it. Take the 2-liter bottle and drop it on your chest. Have somebody do that. I bet it's going to be quite unpleasant. Clearly, on the cap. Okay. Clearly, the dime is going to rip your chest to pieces. So you've just made up that story, right? Now, we know that, if the dime goes in sideways, okay, that's going to make it, a lot more dangerous. And the same is true if I do the same thing on your chest with the 2-liter bottle and I put a dime on the cap and turn it, straight in, you know there's quite a good possibility that it'll puncture. Okay. But it's a dime. You know, so the point is again, you can keep pretending it's a bullet, but it's not. It's not shaped like one. It's not going to hit you like one. And the fact is it does have the same energy. That is, both of them have the same capacity to move molecules. So if you want to explain how the dime has more capacity, like if you want to draw me a picture of a dime and the cap of the bottle and explain how when all the exchanges are added up, that they actually did, the dime made 2,000 times more heat or more energy. 2,000 times. I mean, that's what, if you do there, you can do the momentum math and you get right from one to the other. If you do the kinetic energy math, the fact is the dime going 1,000 miles an hour is supposed to have 2,000 times as much energy. 1,000 times. 1,000 times more energy. Do you think so? Why, again, don't they tear buildings down by shooting dimes into it then? I mean, you know, you could argue, okay, what do I want to tear the building down with? You know, 2-liter bottles going this fast? Or do you think you're really going to have a 1,000 time advantage by shooting dimes at it? You know, anyway. Same momentum, very different kinetic energies. Oh, well, anyways, clearly the dime is going to rip your chest to pieces. So that's clearly not true. So if you spread a .22 caliber slug into the size of a dime, it might not penetrate somebody's skin. Just a fact. Okay, and the water bottle will barely leave a mark. Well, you say it barely will leave a mark. I think it's going to leave a pretty good mark. Go ahead and try it. Please, do the experiment for us all. Why don't you do that? Or why don't you, better yet, because you added this little extra part here. Anyway, same momentum, very different kinetic energies. So says you say that's good science. Good science is this seems like, looks like, oh, it appears, you know, that's good science. When no, good science is, you know, really think about it and go through the scenarios. You know, like I said, hypodermic needle. You really think the dime is going to push the hypodermic needle further than the 2-liter bottle? Okay, not quite as eloquent an example as eating a cupcake or a nail in your eye. So he's bringing up different subjects, which is just plain horseshit. So let's push a nail into your eye. Okay, let's ask that. Which one do you want to push the nail into your eye? Okay, and let's say, because you say the dime has 1,000 times an advantage. Okay, it's 1,000 times more energy. So let's take, you know, let's reduce the energy of the bottle by 1,000. Okay, so now let's do the comparison between the 2-liter bottle with 1,000%. I mean, you know, with, it's joules, right? So we're saying the difference is between 2 joules and 2,000 joules, right? So they say the dime has 2,000 joules. So let's even it out and let's minus 2,000 joules worth of energy, you know, 1,000 from the bottle. And so that means the bottle is now like an ounce. So now we're going to drop an ounce on the nail versus the dime. Which one do you want to hit your nail into your eye? Yeah. So fuck you. I mean, this is just a horse shit. But that was the inspiration. Really appreciate all your videos. Yeah, just fuck you. Okay, so that comment will be deleted. I'll remove it, you know, just so I don't want to remove the rest of his comments, because not all of them are assholey. I mean, some of them get to the point, you know, but they just can't help themselves. These are all sock accounts, you know, so it's probably just a cowboy playing his game. But anyway, this is the one, you know, they're always doing this shit. Okay, let's do this stupid, idiotic formula, and I'll explain why they're getting this fundamentally wrong. You know, why they can't do logic or math worth shit. It's that simple. Because they don't even understand the difference. I mean, I've said it so many times. Gravity is a constant force. Okay, so it's very different than, you know, a force that something has, like a bullet. A bullet only has the energy once. It can only deliver one amount of energy. Where gravity isn't applying joules of energy, once, it keeps applying it. It keeps pushing you into the chair, okay? The joules keep adding up in a way, in the terms of what is actually happening to the physical structures. The physical structures are enduring a reoccurring energy, not just you hit them one time and that's it. So in a sense, you have to understand when you're saying a force, okay, there's no point in saying, okay, so something has a velocity, but nothing's pushing it. So there's a bullet flying through space, and it hits something. All of its energy is just the energy one time. That's all it's got. Okay, where in these other examples like gravity, you keep pushing the object. Okay, it keeps getting pushed. It's pushed. It's pushed. And even when it lands, it's still being pushed. It's still being pushed. It's still being pushed. So gravity is a constant force. All right, so it matters that you're applying it over a distance. Right? So distance matters when you're applying a force. It doesn't matter when it only has the one force. It only has the one amount of energy, the one set. Where if you're going to keep applying the force, that's completely different. Okay, so you can see that in his math here, where where they have this work equation. So obviously in none of these circumstances does this work equation apply. So they change F equals ma, okay, into work, okay, equals ma times distance. So now they've got ma times distance, because the work would be how hard are you pushing constantly. So none of these examples is distance relevant. So you won't be multiplying times distance. Okay, it's not like gravity, where gravity keeps hitting something. When it's pushing it down, it keeps hitting it. It keeps hitting it. It keeps hitting it. It keeps hitting it. It's doing work the whole time it's falling. Where the bullet, the work happens once. One pile of work, that's all there is. There's no more work. Distance is now irrelevant. The bullet has the energy, and there's no work involved. Okay, until it hits something, it's not doing any work. There's no distance. So there is no such thing in the equation. All right, so then they'd convert it into distance. All right, equals. So now this is where they say velocity squared, right? Yeah. So then they'll pretend that they're measuring the distance based on the velocity initial squared plus the velocity final squared, okay, and then they divide it by 2a, I believe, right? Something like that. Well, they're multiplying it by 2a for whatever reason. Anyway, so the point you can see, this is where they're squaring the velocities, right? So they're supposed to be minusing something, and they've squared them, all right? The square is basically them implying that the force is constant. The reason why the work formula works is because it's counting the fact that it's a constant force that you keep applying. Okay, so you're adding force with distance. It's 500 watts here, and then there's 500 more watts, and then there's 500 more watts, and then it's 500 more watts. Where the bullet just has the 500 watts. It doesn't have a continuous source of wattage. And that's where this whole formula thing breaks down. That's why these squares are here. So the squares don't belong here, because this isn't a work function, and we're not calculating how much work it would be if we were pushing it constantly. We're just calculating the difference between the velocities. All you want to know for the only way distance is relevant is you're just saying, to calculate velocity, I just have to know how fast was it going when it started, which would be 0. How fast is it going for its final velocity, which we could say is 15. There's absolutely no reason to square it. That's our velocity, 15. That's the net velocity, 15. Okay, so we've already figured out what v equals. So why would we do this? There'd be no reason to do that. So that's where it all goes wrong. Because as soon as they start squaring something, then they find an excuse to do it. Then they leave everything squared. All right, so we've already been through this in different versions. So then they say if VI equals 0, then W, work. So again, there is no constant work. There's only the initial work of imposing the force. You can't do this work like when a bowling ball hits a pin. You understand the pin leaves immediately. There's no work function. There's no distance. There's no any of that stuff. So obviously there's no squaring involved. You're just going to calculate the velocity the pin leaves at, which is going to be the same velocity the ball's traveling at. Because as soon as the pin leaves, as soon as the pin's going the same speed as the ball, like one tiny bit faster than the ball, then obviously the pin can't get any more energy from the ball, right? You do understand, if I have something moving and it hits something, and now it starts moving it, as soon as this is going a little tiny bit faster than this, it can't give it any more energy. All right. So, so he says work equals ma, which would be mass times acceleration times the velocity final squared. So that's where it all goes wrong, right? There's no reason to square the final velocity. None at all. There's no continuing force being applied. There's no reason to square it. So that's where it all goes wrong. Divided by 2a. So and then he says 1/2 mv squared, right, which is 1/2 v times v, right, which is just garbage. Okay, so obviously there isn't any constant work applied on the pin. When a cue ball hits another pool ball, there's no constant work applied by the cue ball. There's no reason to square the velocity. All right. Yeah, so I've answered that, so I'm going to delete it just because I'm not going to bother putting the comment here or put a link to this video or any of that other crap. I've already answered this so many times, but regardless, no. So go ahead and make a rational argument defending this distance argument. First, that you measured the distance, say when a cue ball moves, that you somehow measured how far the cue ball moved when it hit the other ball and gave it all its energy. That would be the only distance that could possibly be relevant. So when did you measure any of those distances? Okay, and when did you calculate the velocity over those distances and square them and do all this stuff? So again, the work function is supposed to be for calculating when you're rolling something constantly, like a snowball, and you want to figure out the work. You have to calculate how much work you're applying over a distance, because that's basically calculating how much energy you're having to put into the snowball. But that's not what any of these circumstances have anything to do with. None of these are constantly applied forces, so we're not calculating total work. All right. Yeah, okay. All right, so what else did I want to get to? So this one, I see you deleted some of my comments, and I pointed out, no, I deleted one of them because it was rude garbage, and then I have indulged you and I let you do all of this crap, and I've answered all of your stupid crap. So none of them will stay on the 3 thought experiment type examples, and so I'll show those in here. So I did answer. So here are the 3, right? So the 8-pound ball having twice as much kinetic energy as the 16-pound ball. No evidence that happens in the real world. Okay, then the obvious one I just explained, shooting 2 objects up. They have to leave with inverse velocities. If I have inverse masses, they have to leave with inverse velocities. By their theory, the light object has twice as much energy when the objects leave. Even though the same force pushed them, it has to have twice as much energy by their formula. And yet when they land, they'll still just compress the springs exactly the same amount. Completely consistent with momentum being the right answer and kinetic energy being nonsense. And then the train argument again is just so obvious. Okay, they think a 5-ton train going 10 miles an hour has more energy than a 10-ton train going 5 miles an hour. Zero evidence of that. Never, ever, ever will they be able to collect that extra energy or that energy differential. They'll never show it to exist. I can plow the 10-ton train going 5 miles an hour into a spring, then I can lock the spring, I can put the 5-ton train on there, and it will be shot at 10 miles an hour. That's the facts. And it's a decisive proof, in my opinion. It ends the conversation. So until they prove in some way one of these premises wrong, one of these statements wrong, till they prove that something leaves at 1.4 the velocity, that somehow the same energy can't make it go twice as fast, that somehow the same joules of compression in the spring won't make the cart fly the right speed. Now, I showed the Professor Lewin video, that which is pretty decisive. I put a one mass cart and a one mass cart between a spring, compressed the same amount. They both leave at exactly the same speed, same joules. I put a twice as heavy one on one side and a one mass one on the other side. This one leaves with exactly the same joules as the previous cart, and this one leaves going half as fast. Same joules though, twice as massive, same inversion of the formula. They all have the same momentum. So it just decisively proves this 1.4 thing doesn't happen. All right, so they keep claiming it. They have no evidence for it. And, the argument really should be over. Okay. So I really don't know if any of these comments are worth reading. Their arguments are really bad. So if you want to read them, you can read them. But it's basically just already I've already dealt with them. All right, so so we'll move on to, there's one more comment on the message board thing, the Quora thing, but I think I'll just do the momentum argument. So I'll take a pause and we'll do that. There, it should be back. All right, so I just remembered something that should be put into the mix. So when you initially launch something with a spring, the trick is you need something between the spring and the object, because technically if you put a heavy enough mass on a spring, the masses themselves weigh something, so the spring will be compressed a little more or a little less based on the initial mass. So if I have a 2 mass obviously and a 1 mass, the weight of the object itself will cause some compression in the spring, okay, and so there'll be some unevenness. So the spring has to be much stiffer than the weights of the masses being put on it. So if you're right at the margin, you'll change how much the spring can obviously push back, because gravity is constantly pushing on the objects, and obviously the heavier, the more atoms moving, okay, more mass being pushed constantly by gravity will compress one spring initially more than the other spring. Okay, but if we use some other mechanism, like we hold the 2 balls, with a little plunger, okay, and so the plunger doesn't hit until the energy is released. So the ball's being held by this structure and this structure, and so just to be precise, like I said, this isn't really going to change the experiment much, but just to be precise. And then so you have them sitting on top of something else that's absorbing their initial mass, and then you just shoot something at them with a spring, the same piston, shoot at them with the spring, then you're ensuring that you're putting the same energy into them. So that's all. I just wanted to make that verification. But I guess, like I said, for most of these experiments, this part isn't going to matter too much. So the part I really wanted to go through was just the fact of what happens when something's moving. Okay, so I move something, let's just move it sideways and just forget about gravity. You can understand that it hits air molecules. So there's little air molecules. So it plows into them, and what does it do? It exchanges its momentum, okay, its force, its velocity times its mass, okay, with the environment. All right, and it gives the little molecules its speed. So it can hit one, and if the thing is going this way, it can change its direction to this way, okay, and make exchanges, constantly make exchanges. It gives it energy, and it exchanges the energy with the object. So it'll constantly be doing that. So that would be heat. That would be losses to the environment, and it'll degrade the momentum. So we know something's going to slow down. So we know that it's total momentum. We could say it had, let's start it off with 100 joules of energy. Okay, so just getting from here to there, all right, is going to cost it some energy. And by the time it gets here, they could say it has 99 joules of energy, because it gave energy to the little molecules it hit. All right, And then what's going to happen if, let's say, it's hitting pins or some other kind of stuff? Well, it's going a velocity. So let's just say it's going 50 miles an hour and it hits a pin. Well, what's it going to do with that pin? It's going to push it, okay? And it's going to push it. You can only push it 50 miles an hour as a maximum. But the fact is it gives a joule away. That means it's only going, say, 49 miles an hour. Well, we should start with 100, and then we'll have 100. So we'll just say 100 joules. It's starting with. So when it gets to the pins, it has 100 joules. Okay. And it can only give away them in terms of its velocity. So when it gives away some velocity, when it gives some velocity to this object, so now the object's going 1 mile an hour, then it's going to go 2, 3, 5. It's going to go very quickly to the maximum speed. But it has to push each one of its mass units. So let's say the pin has a mass of 5, and this has a mass of 10. Well, we could use 3 or some other numbers, of course. That might be more close to like pins in a bowling alley. So if the pin was a 3, okay, and the ball's a 10, what's going to happen is as it's giving its energy away, it's going to be reducing its speed. So as it gives away joules, you know, say it's giving away 4 of them, okay, that means this speed has to go down. So now it's only going 92 miles an hour. So now the maximum speed it can give this is only 92. And as it gives away more of its energy, it's got to slow down. So by the time it gives it its fair complement, which is its, you know, let's say it's 3, so it's 1/3 the weight of the bowling ball. So it can only give away 1/3 of its reduced velocity. So the total velocity, it started with 100, it can probably only give this 70 miles an hour, okay, and it cost it 1/4 of its energy. So now it's down to 72, let's say. So now it's only going 72 miles an hour. So now it hits the next pin, and the maximum speed it can give the next pin is 72 miles an hour. Now it can't give it that because it's going to go through the same process of reduction. So now this one's probably only going to go away at 50. And now this is down to 49. Okay, it's down to 49 joules. And then it's going to hit the next pin, and the maximum speed is 49 miles per hour, right, that it can give. But it can't give that because as it starts to give it, it's reducing its speed. So its maximum speed, by the time it's put all the joules, okay, into the pin, by the time it's given it, you know, whatever, 30 joules worth, its speed's going to be much reduced. And so now we're down to like 25 miles an hour. So this pin will leave at 25 miles an hour, or even less. You could say 22, something like that. And now the object is only going 21 miles an hour. So by the time it gets to the 4th pin, it can only give the maximum of 24, but it's going to give, you know, 22, but it's really going to give only, you know, whatever, 10. Okay, so now we're down to 10 miles an hour. So by the 4th pin, it's down to 10 miles an hour. And the ball's now going only 9 miles an hour. So now it's really slowed down. You know, it's really losing velocity. And so now the maximum you give the 5th pin is this little lame amount. So, you know, you have to trace it, okay? There's only so much energy it can give the world. It can't give it this kinetic energy, fake, you know, extra energy stuff. All it has is its momentum. And everything it moves has to come out of that momentum. And as I pointed out, you have a choice, right? You can plow something into clay and convert everything, you know, into movement of the atoms. Okay, basically heat. All right, you'll move the atoms in all kinds of weird ways, and so all of the energy will be used up moving atoms in the clay, deforming the clay and essentially creating heat. Or you can hit something hard and give it the momentum, and then it can hit a piece of clay and turn it all into heat. So the point is you can transfer the energy into the movement of a big thing, or you can transfer it into the movement of a little thing. All right, but you can't do both. You can certainly hit it into a big thing and then have the big thing hit a little thing. Okay, so you can transfer it, I guess I should draw a big thing. You can transfer it to another big thing and then have that big thing transferred into a little thing. But you can't go from big thing to little thing, heat, and then hit another thing with it. You know, that won't work. So, but it's always going to kind of turn into this little thing, right? Everything, you hit something a little smaller, like the pins end up hitting surfaces, bang into stuff, causing the clay kind of deformation, heat, noise, sounds, all kinds of stuff. So every time you do a transfer, so every time you go from, you know, one object into another object, you know, you're going to hit 5 pins or whatever, and all those pins are going to leave at different velocities, and they're going to hit different things, and as they hit different things, they're going to dissipate the energy into smaller and smaller movement of smaller and smaller things. So it's just going to dissipate into the environment, but there's only so much movement capable. There's only so many. The joule is basically just telling you it's a quantity of motion, and you're just going to give that quantity of motion to all these different things, and eventually, like I said in the bowling, you throw the ball, the pins move, then everything stops. And all you have left is the fact that, well, there's still sound bouncing around, the echo. You know, you have some heat in the air, and you have some impact locations on the floor and the walls that are now, you know, a few degrees Celsius warmer, and that's what it's all been turned into. So all the movement got turned into places where the atoms are jiggling and they're hot. So there's little places where the atoms are jiggling and hot. So if you had like a thermal camera or something and you made the alley very cold, you know, you could hit the ball and you'd see the pins get a little bit warmer, and you'd see the walls get a little warmer. You'd see the momentum being transferred into what all it can do, which is transfer the momentum, the energy. All there is the momentum. You transfer the momentum into the pins transfer it into the walls and the floor and the ceiling and all that crap. That's it. That's all there is. There's no kinetic energy. There's no extra place you can get extra energy from to cause all kinds of extra interactions. All you have is the momentum, and eventually, I mean, all you can do is transfer it efficiently, you know, into a bigger object, or lose it in a sense that it goes into very inefficient movement, that is, movements in all kinds of different directions, and you'll no longer be able to trace the movement because it'll be broken into so many little pieces going in so many different directions. But that's it. That's probably enough. Yeah. So there's no reasoning behind this. Again, this theory doesn't solve anything that was broken. There was nothing broken with momentum. Momentum works perfectly fine. So again, I can keep asking somebody to show me the experiment where we prove that momentum gets wrong answers. And there's no such experiment. Newton did just fine documenting how the motion of Halley's Comet, all these things in space, he documented it just fine, just using momentum. There was nothing broken. So why did you break it with this fake energy that doesn't have any meaning, that you can't trace through the environment because it's way too much? It's a silly exaggeration of the reality. There's no accounting for it. You can't catch it. Again, in all the experiments you demonstrated, again, do you really think if I take a 10-ton train going 5 miles an hour and a 5-ton train going 10 miles an hour and I plow them into a spring, do you really think the lighter train is going to compress the spring more? That it has more energy? If I give the heavy train, if I make it have the same kinetic energy, if I make the lighter train, if I make the heavy train have the same kinetic energy, would you really want it driving a nail in your eye? I mean, to make this argument, I mean, which one would you prefer? If I was to balance them, give them the same kinetic energy, that is, make the train go 1.4 times as fast. Do you really think your eye is going to be better off if I make it go faster? I make the slower train go faster to make the kinetic energy equal. You want that heavier train plowing the nail in your eye? I don't think so. So it's, they have equal energies, and there's just no room for this fake notion of some, extra energy or less energy. No reason to think the 10-ton train has less energy, and no reason to think the lighter train going faster has more. There's no good reasoning. There's no way to explain how you can't collect the extra energy. I mean, realistically, you got to know. I mean, I plow the 10-ton train going 5 miles an hour into a spring. Then I lock the spring, and then I put the 5-ton train on the spring. You know it's going to give you the same amount of energy back. You got to know it. You got to know there's good reason for you to not be as confident as you are in this silly theory. I mean, again, I've gone over and over and over the history. It's a terrible history. Can't you acknowledge that? That there was no good reasoning behind it. The motivations were all bad scientific motivations. It was all to try to defeat Newton. It wasn't about anything else. Leibniz was overt in his statements about how Newton's physics was too austere, too unreligious. It was invented for very poor reasons, and it was defended for very poor reasons by, loop-de-doos who just basically wanted the universe to be more interesting than it was. They weren't motivated to tell the truth. They were clearly quote mining the evidence to tell their story. It wasn't about facts. It wasn't about good science. It was about, let's find some clay experiments that'll fool people. It was about Ken Wheeler with his Faro cell. It wasn't about the truth. And just understand that's what you're defending. It's a terrible history, and you're defending it. Because you don't, number one, even acknowledge it. You won't even acknowledge the fact that this is not good science. That no process was good science here. And it's certainly not good science to use a work formula that's calculating force that's continuous and use that to tell me how much energy a bullet has. Bullshit. Okay, I say to that. There's nothing constantly pushing the bullet. It has one clump of force, and that's it. That's all it's got. And when it's gone, it's gone. It's just like the spring argument, right? I mean, something falls and, well, that's probably not the best example because gravity just keeps pushing you very weakly. Obviously, the velocity you accumulate because gravity is constantly pushing you is much greater than the force that gravity is actually adding per second. Gravity's weakly pushing you like this, and it just keeps pushing you. All those little pushes just keep adding. But anyway, all right, it's probably enough of a video. We'll save the other thing, the Quora thing, for a separate video and just do this as a comment video. Yeah. All right. So I'll put probably the 3 statements: bowling balls, shooting things into gravity, and the train thing. Put them on the website or something, and just say those are the thought experiments you have to argue. Now, it'd be nice if we had if somebody actually did these experiments, right? That would be great if we could just show the experiment being done. Now, Stephen Bro did part of it. I mean, he did shoot things, to unequal masses into springs, and he did get the results I'm claiming. But he claims there's something wrong with that experiment, so we won't force that to be good evidence. And clearly, he wasn't very careful in how he did his experiment, so we could say that maybe he fucked that up. And that's the only reason why it agreed with me. But the truth is it is the truth, okay? I mean, you can pretend that it's only 1.4 the velocity, but it isn't. All right. So anyway. So till the next time and such. That's really enough, I think. Yeah. I think I'm satisfied. Yeah, that's good enough. So till the next time and such. This afternoon, a DraftScience video presentation.